this state in the Fock state in the Fock representation and check that this is produced. Okay. So, now this function is just a function. It is no different from the function that we write down over here in conventional quantum mechanics, and they can be moved around across the operator because this is just a multiplicative thing. So now I'm going to write, there's an integral part d of r prime. Okay, and then is these 4 wave function operators, which we need to consider their order. So I'm not going to write them down. So over here. Okay. So now let's try to move them across. Okay. Let's try to use this product term to operate on this thing. Okay. Yeah. It's not that difficult, okay, but it's a bit tedious. Okay, so that's the product. Let me leave this factor out here. All the way to R big. Okay, so the strategy here is first, let's move this across. Okay, produce a bunch of delta functions. Okay, and then instead of moving this across and then this across, let's notice that this is, remember we defined that local density thing. This basically counts whether there are states present at the R prime location. So this is just going to give us some delta function. Okay? And then we move this across. Right? So the first step is to move this across. Let's write down one term. So thinking about this combination, this using the anti-commutation relation, this goes to I delta of R minus R1, right? And let's write down explicitly, we have changed the order of the operators once. So this is minus 1 to the 1's power, because every time we change the order of operators, we acquire a minus sign, as required by the commutation relation. And then we have moved this across R1. I'm not going to write the vectors anymore. There's too much to write. And then this. So once this is done, this term gives you the delta function, and then over here the first, and then what's left, the R1 is missing from here, right? Okay. And then over here, this term, nothing really changed, just that we've inserted minus sign here, and also we've inserted this R in between R1 and R2. And the next thing to do with this term is eventually we want to move this all the way across. And every time we do that, we want to move this all the way across until when it hits this vacuum state. Okay? And every time we do that, we're going to produce a factor like this. Okay? But then the sign of this, the term that's left, is dependent on the position, the number of times that we have switched the order of the wave function operators. Right? So combining all of that. Okay. So we're going to move R to every possible n location. Okay, to every possible n location. So it's n equals to 1 to n. And then each of them is associated with a delta function, matching the R coordinate to the nth coordinate. Okay? And then to move R to the nth location, how many times do we move it? We move it by n minus 1. So this is minus 1 to the n minus 1's power. Okay, but actually, this factor gets thrown away later because we're going to move it back again. Because we have this, we need to move this to the nth position again, so to recover the state this. Okay, so it actually gets thrown away. But we attach it anyhow. Okay. And then what's left is, am I right? So this is, all of these operators are present, but the nth one is missing. Correct? Okay. In this one, we just have this with the first one missing. Right? And okay, and by analogy, the nth one is going to be missing. All right. So now, okay, all these have been moved to the front because they are just factors. They're just functions. Okay. This one we move across and it sees all these. Okay. So what this is going to pick up is to see whether there's a particle. There's some kind of some particle at the position r prime. Okay. And actually, there will be particles at r1, r2, rn minus 1, rn plus 1, all the way to rn, except at rn, right? Because the rn dagger is missing from here. So this state is the state that excludes a particle at rn. Okay. So what's the action of this on this? It's another bunch of delta functions, excluding the n equals to the m equal to n case. So let me write this as 1 over this factor here. And this is just backdating right now. Okay. The summation of these delta functions. Okay. And then this is going to produce another tray of delta functions with index by m. Okay. And all we require is that m is not equal to n because the n state is not present in this string, right? All the way to n. Okay. And then it's delta r prime minus rm. All right. And then again we have this. Nothing changed here. Right? So copy this thing down to here in your notes. Right? Okay. So now all we need to do is move this across. Okay? And that's really simple because now they are all daggers. They're all creation operators. And to move creation operators across, all we do is we add a minus sign. Okay? And now if I want to move the r to the nth position, I need to move it n minus 1 times. Okay, so we acquire a minus 1 to the n minus 1 power. And it sees this. Right? So this is plus 1 to the n minus 1 power. And it's just gone. Right? So this factor is gone after we move it across. Okay, so what was that again? Let me do it explicitly. Okay, so we have square root of n sigma n equals to 1. I'm excluding the vector of sign. Sigma n not equal to n r prime minus rm. Okay, and there is a minus 1 to the n minus 1's power. And this wave function operator in terms of at r is appearing at the front of the list. Okay. And then over here we have r1, rn minus 1. N plus 1. correct? That was what we got over there, right? So now what we need to do is we want to recover a state like this, like this. So basically we need to make this, correctly order them. Let me just finish. So we want to correctly order them, and the order is done by moving this to the nth position. And how many times this is done? Okay, n minus 1 times. Right, so we acquire a minus 1 to the n minus 1 power, which cancels with this factor. Okay. So other than a index difference, okay, what we have is 1 over square root of n. So now if I take this factor over here, now they will contribute to the state with R1, R2, and in place of Rn we have R, right? This state. And then in front we have sigma n equals to 1 to 3. And then this, I can combine these two summations, and you'll see that these two summations is really no different from here. I just sum over all the n not equal to m. Okay. So n not equal to m. They're exactly the same. All right. So now what we need to do is we need to do the integral. Okay. Remember we have still this factor over here. Okay. And the integral over r and r prime, okay, I'm going to remove those delta functions and give you a replacement of the r prime and r with n and m respectively, right? Okay. And then you get that they agree. So this is true for any number of parts. Okay. Yeah. Was this clear? Okay. All right, good. And to look at a specific example, I think in the lecture notes we give you an example of three particles and 2 particles explicitly. But you can also take a look at that. Okay. Are we out of time? Yeah, I guess so.